So with that, we go on to the next module in which we'll talk about unsupervised pre-training. Okay. So this work which I'm going to talk about, we're trying to understand what has changed since the late 90s or the early 2000s. How did deep learning become so popular despite this problem with training them, right? This problem was there, so what happened to solve it, right? And this field actually got revived by this seminal work by Hinton and others in 2006, okay? So let's see what that idea was, okay? So this was the idea of unsupervised pre-training. In the original paper, they introduced this idea in the context of something known as RBMs, which we'll do in the last 33% of the course. But we could do the same with autoencoders, which we have already done. So in this lecture, I'm going to talk about this idea in the context of autoencoders, okay? So consider a deep neural network shown in this figure. So the module name and the idea was unsupervised pre-training. So that itself is a giveaway of what is going to happen, okay? So suppose this is the deep neural network that I have designed for a particular classification task. So what it is doing is taking an input, which is the red colored neurons that you see at the input. It has 4 hidden layers. That means it's 4-layer deep. And then you have the output layer, which tells you whether positive or negative, right? That's the network that I have. And I know that this is hard to train such a network. The loss will not converge and I'll not get anything meaningful. So what these guys suggested is that forget about the supervised criteria that you have. That means you're trying to minimize the classification loss. Just forget about that. Just take the first 2 layers of this network, okay, which is X and H1, right? So you take the original input X, you feed it to some transformations and you get the hidden representation H1. And now try to reconstruct X from H1. What is this? Autoencoder, okay? What's the objective of the autoencoder? It is exactly this. So for each of the M training examples, look at each of the dimensions of your input and minimize the square difference between the actual input and the predicted input, right? Is that fine? That's what an autoencoder does. So this is what they suggested. Okay, so right now I'm not telling you why this makes sense and all that. That's what we'll do later. Right now I'm just telling you the trick. Then we'll analyze why that trick works, okay? And why is this objective unsupervised? Because we are not using any labels. We're just giving an input and we're just reconstructing the input. We only have X's, we don't have Y's. Of course, eventually we'll use the Y, but at this stage, when I'm calling it unsupervised pre-training, I'm not using the Y, okay? Okay. Now, at the end of this, what would happen? Yeah, what would H1 learn? It will learn an abstract representation of X. Was that our original task? No. What were we interested in? In the classification task. But we are doing something very different. Why? We'll see. Okay. Okay. Now guess what would the next step be? Does this make sense? Now at the end of the first unsupervised pre-training, I have ensured that H1, which is this layer, has learned some abstract representation of the input. Right? And that I know from the autoencoder, the autoencoder which we have learned earlier, right? That it learns an abstract representation of the input. Now I have this. So that means given an input, I know how to compute an abstract representation and I'm also sure that it captures the important characteristics of the data. I'll just repeat this process. I know that I have 4 layers in my original network. So I'll now take H1, try to compute H2 and then reconstruct H1 from it. So in effect, what am I doing in plain English? Learning an even more abstract representation of the input. So H1 was already one abstract representation. Now from this, I'm learning an even more abstract representation. And does the objective function make sense? Right? All I've done is replaced X by H1, right? In both these places. Okay, the rest of it is the same for all the training examples for all the dimensions. And throughout, I'm assuming that we have n neurons in every layer, including the input layer. Okay, is that fine? Now what would the next step be? Fix the weights in H1 layer, fix the weights in H2 layer, and now try to reconstruct H2 from this H2, right? And in this way, we'll continue and learn all the hidden representations. Does that look okay, right? So at least this much we believe, right? Because we know that autoencoder works, and we're just using an autoencoder and we're using it incrementally. from every abstract representation, learn an even more abstract representation. Okay. Now at the end of this, what will I do? What was my original task? Classification. So what will I do? What is the network that I have when I finish this unsupervised pre-training? Tell me, of the diagrams that you see on the slide, how much of the network would I have? Right? Everything except the green output layer, right? Because the last step would be take take H3 and reconstruct H3 from it, and in the process learn H4, right? Is that clear? So I would have learned till that point, and now what I'm going to do is something very simple. After this layer-wise pre-training is done, I'll add my output layer. Now all the weights in my network for every layer have been initialized, and they have been initialized in a way that that layer learns a good abstract representation of the input, right? That's the thing that we have achieved at the end of unsupervised pre-training, that every layer has learned and more and more abstract representation of the input, right? Now I'll keep all these weights initialized to whatever I learned in the pre-training setup. Does that make sense? So that means instead of taking this big network with the output layer and initializing the weights randomly, I'm just going to use whatever weights I learned using the unsupervised pre-training. Okay? So can you tell me what has happened in terms of the error surface and so on? Or my movement in the WB plane, or in this case, this very high dimensional W plane. I've reached some configuration for the W's where I know that each of these layers is a good meaningful representation of my original input. Right? Is that a fair statement in English? How many of you agree with this? Anyone has any questions at this point? One layer weights. That's what you do in answer. Because if you train all the four, then you are again entering the same problem which you had earlier, right? You can't back propagate through all the four layers, because now it's a deep network and we know that doesn't work. So at every layer you fix whatever you have learned so far, and at a time you are training only one layer. So that's one interesting way of looking at it, right? You know that the deep neural network with 4 layers was not trainable. So now we have reduced it to 1 layer at a time. And you know that 1 layer at a time works, right? Is that fine? Okay. Now I will add the output layer, and what will I do? Train the weights of the... I'll not just do that, I'll fine tune the entire network. That means I'll train the weights of the output layer, and I'll also fine tune the entire network. But now I'm contradicting myself. I just gave an answer to him that again I'm doing this deep training, and I know that deep training doesn't work. But this actually works. Do you get the difference? Right? One is that when I take this big network, I start from random weight initialization and try to train it. That's the story from 1986 to 2006, that in most cases these networks did not converge, right? So now in 2006 someone came up with this idea of unsupervised pre-training, where you train the network 1 layer at a time. You do up till the last layer. Now you add the output layer and then fine tune the entire network. That means back propagate over the entire network. Is the setup clear to everyone? How many of you understand the setup? Okay. Now, again, when I'm doing the last step, which is known as fine tuning, I have to back propagate over the entire network, because I'm saying I'll adjust all the weights. But suddenly this works as compared to starting from scratch. Right? You see the problem, and you see why this is important then? Because this has now given you a way of training deep neural networks. I've still not told you why it works. We'll delve into it, but not really give any concrete answers, because concrete answers don't exist. But we'll at least try to get some intuitions behind why it works. Okay? So you get the setup now, that this is what was happening till 1986 to 2006, and now with this idea, suddenly deep neural networks were being able to train well. Okay? So in effect, what we have done is, we have initialized the weights of the network using the unsupervised objective, right? So now instead of starting with random weights, we have some weights which cater to the unsupervised objective that we had, and the unsupervised objective was this layer-wise reconstruction. So that's what has happened in plain English. Is that fine? Everyone gets that? Okay. Now the question is, why does this work better? And I give you 2 options, and I want you to think about both these options. Okay? Is it because of better optimization, or is it because of better generalization? No, that's not an option. But of course, we'll relate it to that. But given these two, I want you to think whether there's any difference between these two statements or not. That's the first thing I want you to see. How many of you get the difference between these two statements? Not many. Why is it so? What does optimization deal with? Dash data or dash data? The answer you can give dash, right? Dash 1 data or dash 2 data? What does optimization deal with? Training data. Optimization depends on training data. What does generalization depend on? Test data. So you get the difference between these two questions. Okay? Fine? Okay? So let's try to answer this. Again, here, right, this is 2006 to 2009 period that I'm going to talk about. There are some answers, and just bear with me, I'll give you those answers. Some of them will not look very convincing. But what happened after that, or as a result of these investigations, that's more important, right? Whether these answers make sense or not, they'll make sense to an extent. I'm not saying that they'll just be bluffing, but it will not be very convincing because there's no theory behind it, right? So what is convincing if I give you a proof that this plus this is equal to that, right? Then if I give you a proof and everything, you don't have any other questions. That's not what I'm going to give you. I'm going to give you some intuitions because that's all these existing works from 2006 to 2009 had. And then I'll make a commentary on that which will lead us to some other things, okay? So just bear with me for a few minutes, right? That's the optimization problem. If that was the case, I'll just come to that, okay? That's what I'm going to talk about, okay? So so these are the two questions that we're dealing with, right? And the answer is depends. So we'll see what it is. So let's first examine the case when it is because of better optimization. So let's first understand what is the meaning of this question. When I ask, is it because of better optimization, then the question that I'm asking you is that the first setup where I was trying to train everything from scratch compared to the second setup where I had this unsupervised pre-training, is it that the optimization problem becomes easier in the second setup? Now if the optimization problem becomes easier, what do I actually mean by that? That I was able to drive the dash to dash, loss to zero, right? So is it that this is the optimization problem that we were interested in, okay? So is it the case that in the absence of unsupervised pre-training, we are not able to drive the loss to zero for the training data, and hence poor optimization, right? That if we don't do this unsupervised pre-training, even for the training data, we cannot drive the loss to zero. That means our optimization problem itself is not working properly, right? I mean, the problem is fine, but the solution is not good. Do you get that? Do you understand what is the subtle meaning of this? How many of you get this? So let us see this in more detail, right? So the error surface of the supervised objective of a deep neural network is highly non-convex, right? It looks something like this or even nastier than this. And in particular, it has many hills and plateaus and valleys. We saw this even in the toy examples that we were dealing with, right? And given the large capacity of deep neural networks, it is still easy to land in one of these zero error regions. On what basis am I making this statement? Which theorem? Universal approximation theorem, right? That's what universal approximation theorem told us. In fact, there's this study, the paper which has been cited, it showed that if the last tier has a very large capacity, okay, then you can drive the loss to zero even without pre-training. Do you get the meaning of this? What does this mean? So I have the input, I have a series of hidden layers. What do I mean by the last layer has a lot of capacity? What do I mean by that? It has a lot of dash parameters. Now how do I create these parameters? I'll just grow the size of the last hidden layer, right? And using that, then I'll predict this one, y. How many of you get this? Please raise your hands. Okay, good. So that's how I could increase. So that's exactly what they did. They took a very deep neural network and made sure that the last layer was given a very high capacity. And then they showed that even if you don't do an unsupervised pre-training, you can still drive the training loss to zero, right? So this was hinting that maybe this is not an optimization problem, this is something else, okay? Still not very conclusive, but we'll just go with these studies, okay? All I'm saying is that don't shoot the messenger. This is what the study says, I'm just relaying it back to you, right? And we'll have questions on these, which we'll try to address, okay? But if the capacity of the network is small, then the unsupervised pre-training helps, okay? So if you don't have these large capacity networks, but you have very deep networks, In that case, unsupervised pre-training helps. And this is all empirical observation, right? There's no proof which says that given a capacity K with so much error bound, I can guarantee that the loss would be epsilon within the zero loss and so on. Right? Nothing like that. That's what should have been ideally the case, in which case life is much easier for me. But that's not the case. It's just an empirical study, as are most of the studies done in the period of 2006 to 2009. Okay. So that tells us something about what optimization means and whether this was an optimization problem or not. So let's look at the other question. Is it because of better regularization? So what does regularization do? Oh, you gave the exact answer. It constrains the weights to lie in some regions. It does not allow the weights a lot of freedom, right? And so you know what L1 regularization does. It constrains the weights to this box, and L2 regularization constrains it to this circle. Why? No, why this? I know this, but why? Okay, and why the circle? I'm pretty sure most of you don't know what you're saying, but you're saying the right answer. But anyways, I'll test this in the quiz. Okay, so I've given you another quiz question on camera. So, yeah. So prevents the loss from taking large values. So indeed, pre-training also constrains to the weight to lie in certain regions of the parameter space. Why am I making this statement? What is the meaning of this statement? So I told you that what regularization does. And from there, I'm making this jump and saying that even with pre-training, the same thing happens, that your weights are actually constrained to certain regions of the parameter space. Why am I making this statement? And what are these regions that the weight is constrained to? Think L theta, think omega theta. Any regularization is of the form L theta plus omega theta. Okay? How many of you get that? Very few. Okay, let's see. So it constrains the weight to lie in regions where the characteristics of the data are captured well. Right? That's what unsupervised pre-training does. It is trying to train the network in a way that each layer actually captures the important characteristics of the data. And this is based on our understanding and belief in autoencoders. Okay? So you could actually think of this, that the unsupervised objective that you had for all these layers, that was actually omega theta. You were first trying to optimize omega theta. So in a normal regularization problem, you put L theta and omega theta together, and then you try to balance them. But here you have done it slightly differently. You first gave it omega theta, which is the loss of reconstruction, and you asked it to minimize this loss, okay, across for every layer. Do you get that? How many of you get this? Yeah. No, you're just fine tuning. So no, what that means is that, see, remember that this is a very high dimensional region. Where you initialize makes a lot of difference. So with this unsupervised pre-training, you are at least ending up in region. So you could think of it as a constraint that, okay, move wherever you want to, but start from here, which automatically means that I have outruled some other regions in that parameter space. Do you get that? As you would typically, that would be one thing. And it would also mean that you're starting from there. So with this early stopping and other criteria, you'll not be able to grow much out from here, right? So just, if that makes sense geometrically, from here, you won't be able to move all the way there. You get that? Okay, everyone gets this question and the answer? So you see what the unsupervised objective was, and you also see the difference between a normal regularization and this regularization. In the normal case, you had L theta plus omega theta put together, and then you were trying to minimize the sum of these two. It was a joint optimization. Here you have first done omega theta, ensure that the weights that you learn minimize this objective, and now you add in the supervised objective, which is L theta, right? So now this makes sure that your network cannot be too greedy with respect to L theta, because it has been constrained that it has to first honor the omega theta, because that's where you started, and now from there on it has to decide how to do L theta. Does that make sense? So you see how this is acting as a regularizer? Is that okay? And that links back to your weight initialization thing, right? Okay, fine. So some other experiments have also shown that pre-training is more robust to random initializations. Now what do I mean by that? So in these two graphs that you see here, so this on the x-axis you have the number of layers that you add to your deep neural network, and on the y-axis you have the error that your network gives when you try different initializations, right? So this box actually tells you the variance in the error. So that means I tried training a network with 4 layers, and I tried different initializations, and the error varied in this range. Okay, is that good or bad? What would we want typically? Something which looks like the plot below, right? Where all these variances are little. That means even once you do unsupervised pre-training, right, it is more robust to random initializations. Okay, random initializations of what? The original random initialization, from which point you started the unsupervised pre-training. Okay, because once you have done the unsupervised pre-training, that's your initialization. Everyone gets that? Okay. So these are some, let's see. Okay. So these are some empirical studies, and let me just make a comment on these, right? So what happened from 2006 to 2009 is people showed that, see, this is possible. You can actually train a deep neural network using some of these tricks. We don't have a very clear answer for why this works, right? We could argue different ways of this is optimization, this is regularization, and so on. But I don't have any theory supporting it. There's no proof for why unsupervised pre-training works. All of these are empirical observations. But what it at least established was that it is possible to do this. So now if it is possible to do this, let me see if there are better ways of doing this. Do we actually need to do unsupervised pre-training? Oh, I think it's better regularization. Then why not I try better regularization techniques and see whether that helps. So that led to the evolution of which thing that you have already seen? Yeah. Which regularization technique that you saw in the last class? Dropout. Right? So dropout was something specific to neural networks, which was introduced in the context of neural networks. So this is because people started believing that, okay, it is possible. So let's try even better ways of doing that. So that's how dropout came out, right? Then people said, okay, maybe optimization is the problem. Maybe these earlier algorithms, which up till that point was which algorithm? Gradient descent. Maybe that was not good. So let's try to decide and design better optimization methods. And that led to the evolution of Adam, Adagrad, RMS prop, and so on, right? So all of these studies were not so theoretical in what they were trying to prove. They created this hope, which then led to a lot of prolific work in that field, right? So at least you get the context now, right? So some of these might look, oh, this is one data set, people did experiments on MNIST, but I could have taken a different data set and showed that these results don't hold and so on. You could always ask those questions, but at least what happened is people started believing these and people started questioning that, okay, unsupervised pre-training is one thing, what else can I do? And now what has eventually happened is, today, no one uses unsupervised pre-training, right? That method which led to the revival of this field, and you would have hoped that that would actually survive for many years, that is out now. Hardly anyone uses unsupervised pre-training. It's only used in the context of transfer learning. So what I mean by that is that if you have a model trained for one classification, say classification of images on one data set, right? Now you have a very small amount of data in some other domain. So instead of training a network from scratch for this domain, you will just initialize it with the weights for whatever you have trained on dataset 1. So that's more of transfer learning rather than unsupervised pre-training. So that is still very prevalent. But this reliance on unsupervised training to make sure that the network actually trains, that's largely phased out. Because what has happened since 2006 and 2009 is that we have better optimization algorithms, which are RMS prop, Adagrad, Adam, Eve, and so on, right? Maybe various, and even now that research area is active. As I was saying, just in December, there was a paper which pointed out some flaws in Adam and how to improve it and so on. We have better regularization methods, the most prominent among those being dropout, okay? So these two are things which we have already seen. Today we are going to talk about better activation functions. This is again something which evolved, that maybe sigmoid, tanh are not good, so maybe something else is needed, okay? And then better weight initialization strategies. So then people took this inference, oh, one way of looking at unsupervised pre-training is that it actually initializes the weights in a better way, from where on it becomes easier for me to reach conversions. So why don't I come up with better weight initialization methods itself, instead of relying on this indirect way of initializing the weights. So you get this? So get the whole picture now, what we have been doing in the past few lectures and how it connects to the history and these studies which were done from the period 2006 to 2009. How many of you get the whole picture? Okay, so that's where we are now. So today we are going to talk about better activation functions and better weight initialization methods. Okay.